So this is Physics Required Practical on resistance. We're going to have a look at the factors that affect the resistance of electrical circuits. Firstly, in the length of a wire at constant temperature, and secondly, combination of resistors in series and parallel. So this is activity number 1. We're going to have a look at the resistance in a wire. So the apparatus that we have a power supply, we have a voltmeter here to measure the potential difference, ammeter to measure the current. We have got 5 leads, 2 crocodile clips, and we've got a resistance wire here attached to a meter rule. So if you have a look at the setup, we're using the DC power supply here. So in the positive, I've got a wire going from the positive power pack into the ammeter, and the ammeter into the 0 point on the wire attached with a crocodile clip. From the negative point of the power supply, we've got the other crocodile clip, and that is going to be the one that we move along the wire. So the ammeter is in series and the voltmeter in parallel over the 2 points that are going to be measuring the resistance over the wire. So we're going to start off by placing the negative lead at 10 centimetres. So the positive is at 0, the negative is at 10. Now at all times from now on, guys, you need to make sure that you do not touch that wire. That wire is going to get hot. So if you touch it, there is a risk of burning there. For that very same reason, we're leaving the voltage very low. We've only got it on 1 volt here. We do not need to go any higher than that. Equally, we're going to measure the resistance here by measuring the potential difference and measuring the current. So we're going to turn on the power. We're going to read the readings on both the voltmeter and ammeter, and then we're going to immediately turn the power off to prevent this wire getting too hot. If it does get too hot, it's going to spring off from its stability there, and also there's a risk of it springing in and hurting and flicking in the eye. So make sure that you've got your goggles on, just in case of any eventuality. And we're going to turn that power supply on, take the 2 readings, and then turn it off. So we turn it on, volts 0.72, amps 3.22. We turn it straight off and we record our results. So being careful not to touch the wire, we're then going to take the negative end and we're going to take it to 20 centimetres, and we're going to do the same again with the readings, turning the supply on, quickly taking the readings, turning the supply back off again. And we're going to continue to do that at 30, 40, 50 and 60 centimetres along the length of that ruler, increasing the length of the wire. So once we've collected all our data, we need to work out the resistance. We work out the resistance by dividing the potential difference by the current. So we're going to do 0.72 divided by 3.22, and we're going to do that all the way along till we get our resistance. So we now have our table of results, and we need to plot those onto a graph with resistance on the y-axis and the length of the wire on the x-axis. So we've plotted our results on the graph here, and we need to draw a line of best fit. And we can now see by looking at the graph that the resistance is directly proportional to the length of the wire. So as the length of the wire increases, so too does the resistance. Now, a couple of things that you do want to think about when you're doing this practical is the fact that there will always be a little bit of resistance at 0, because it's very, very difficult to make sure we get the crocodile clips in the exact 0 spot. Another thing that's going to affect this experiment as well is, like I said earlier, that the wire may heat up. That's going to affect the resistance. As the wire heats up, so does the resistance. So this is why, another reason why we turn the equipment off, the power, in between the readings so that the wire doesn't heat up too much. So in the second part of this practical, we're going to have a look at how the arrangement of resistors in series and in parallel affects resistance. So to start with, we're going to have 2 resistors of equal value set up in series. So I'll show you how to get that working, we have our battery. Our battery is going to be connected to the ammeter, positive to positive. The ammeter is going to be connected to one of the resistors. Resistors connected here in series, like so. And then again in series to a switch button and back to the negative part of the battery. The voltmeter we need to connect on either side of the resistors in series. So as we press the switch, we're going to have a look at the values of both the current and the potential difference. So we press the switch and take the readings. The current is 0.06 amps. And the potential difference, 1.46 volts. So using the equation that we know, we can work out our resistance as being the potential difference divided by the current. So in this occasion, the result came to 24.3 ohms. And if you remember, the resistors that we were using in this practical were 10 ohms each. That's 20 ohms in total. If you have a look at that, it's a similar figure. So what we can conclude from this is that the total resistance in a circuit is equal to the addition of both the resistors that are in series. So we have 10 plus 10 is 20. Now the reason that our result is a little bit higher than 20 here could be due to extra resistance in the wires or the connections that we've made there. But the thing we need to remember here is resistors in series add together. So now I'm going to show you how we produce a circuit with the resistors in parallel, not in series. So again, a wire from the positive part of our battery to the ammeter, from the ammeter to one of the resistors. This time, instead of going in series, we're going to connect this in parallel like so, into this one, and then from that position into our switch and into the negative part of the battery. And the voltmeter again is attached here in parallel. So we have the resistors in parallel, the voltmeter in parallel, the ammeter is in series. So again, we're going to press the switch and take some readings. So we can see here that 0.25 is the current and the potential difference 1.33. So again, using our equation, we can work out the resistance with the resistors in parallel. So we have our potential difference over our current, and the result is 5.32 ohms this time. Now you remember that both the resistors we were using were 10 ohms. This is lower than the smallest resistor that was used in the circuit. And this is something that you need to remember. In parallel, the total resistance will always be less than the smallest resistor. Now the reason for this is that when the resistors are in parallel, there are two pathways for the current to take rather than just one through the two resistors. So if there are two pathways for the current to take, there's more total current flowing through the circuit. So if we have a look at our equation again, if the current increases, the resistance must reduce.